So what if you could find critical flaws in a computer chip before it's even built? And what if you could do it using the same powerful tools that we use to test software? Well, today we're digging into a breakthrough technique that does exactly that. It's all about teaching old software tricks to new hardware. All right, let's jump right in. First, we're going to talk about why hardware bugs are such a massive problem. Then we'll get into the big idea, fuzzing hardware itself. After that, we'll see how they actually make it work, and finally, we'll look at the results. And trust me, they're impressive. So to really get this, we need to set the stage. I mean, why is finding a bug in a tiny computer chip so much more serious than, say, finding a bug in an app on your phone? This line from the research paper just says it all, doesn't it? Permanent and potent. Unlike a piece of software, you can't just push out a patch or an update to millions of silicon chips that are already out in the world. The flaw is, quite literally, set in stone. Let me put it this way. A software bug, that's like a typo in a recipe. Annoying, sure, but you just fix it and send out a new version. Easy. But a hardware bug, that's a fundamental flaw in the oven itself. To fix that, you'd have to recall every single oven you've sold. It's a logistical and financial nightmare, and it's how you get these huge, costly recalls of products that are already in millions of homes. So how do you find these critical bugs before it's too late? Well, one of the most powerful techniques in the software world is something called fuzzing. Now, this isn't about just testing for things you expect to happen. Oh no. Fuzzing is like stress testing a system by throwing everything you can possibly imagine at it. Random data, weird inputs, just pure chaos, to see if you can force it to break and reveal some hidden weakness. Okay, so how do you bring that chaotic power to the world of hardware? For years, fuzzing was pretty much a software-only game. But then, some brilliant researchers at the University of Michigan and Google asked a really clever question. Instead of building a whole new fuzzer from scratch just for hardware, what if we could just make the hardware designs look like software? I mean, think about it. The software community has spent decades, literally decades, perfecting these automated bug-finding engines. They are incredibly smart, super efficient, and they've already found millions of vulnerabilities in the software we use every day. But here's the catch. These amazing software fuzzers don't speak the language of hardware design. They're built to analyze code that a computer can run, not the complex blueprints, the registered transfer level, or RTL, that describes the actual physical layout of a chip. And this, right here, this is the core of the breakthrough. It's so elegant. Instead of trying to reinvent the wheel for hardware, they just translate the hardware blueprint into a software model. And once it's speaking a language the fuzzer can understand, they can unleash all these mature, powerful tools on it to find bugs before a single piece of silicon ever gets made. This isn't just about saving a bunch of money, it's about building more secure, more reliable technology from the ground up. Okay, so this all sounds fantastic in theory, right? But how do you actually do it? How do you take a super complex hardware design and turn it into a piece of software that a fuzzer can actually test? Well, the key is creating something called a hardware simulation binary, or HSB. And this isn't just some rough sketch. We're talking about a software program, usually written in C++, that behaves cycle for cycle exactly like the final chip would. It's a perfect digital twin. And you know what's really cool about this? They're not using some crazy expensive proprietary tools. This whole system is built on open source software. The magic trick is performed by a compiler called Verilator, which takes those standard hardware design files and automatically converts them into that high-performance C++ model. Now this lays out the entire automated workflow. You can see it all in action. It starts with that translation we just talked about. Then the model gets what's called instrumented, which is just a fancy way of saying they add little hooks into the code so the fuzzer can see which parts of the design it's hitting. From there, the software fuzzer just takes over, running wild, intelligently changing inputs to find crashes. And every crash, that's a potential bug. It's a powerful, completely hands-off process. But wait, how do you make this work for any piece of hardware? You can't write a new test for every single little component. Well, that's where the secret sauce comes in, something they call a bus-centric harness. Just think of it like a universal adapter. You see, inside a chip, most of the components talk to each other over a standard pathway, kind of like a highway, called a bus. This harness is designed to plug right into that highway. That means the fuzzer can test any component connected to it without needing a special setup. It makes the whole thing incredibly scalable. So, here it is, the big question. Does all of this cleverness, all this translation and automation actually pay off in the end? Well, let's take a look at the results because, frankly, they are staggering. First up, let's talk about speed. Compared to the old school traditional random testing methods, this new approach got to the same level of test coverage up to 2 orders of magnitude faster. That's not 10% faster, not 20% faster. That is 100 times faster. And it's not just faster, it's smarter. Because the fuzzer gets feedback, it actively hunts for parts of the design that haven't been tested yet. The result? It achieved almost 27% better line coverage than previous, more complicated hardware-specific fuzzers. It just plain tests more of the chip. And here's the bottom line. The researchers took 5 different hardware blocks from Google's open-source security chip OpenTitan, and they hid bugs inside them. Some were real-world bugs, some were synthetic. This system found every single one. 5 for 5. That proves this method isn't just fast and thorough, it's incredibly effective. So let's just put this all together, shall we? By basically reframing the problem, by saying let's make hardware look like software, this approach created a verification system that is faster, deeper, and way more effective. And because it's all built on open source tools, it's accessible to everyone, not just giant corporations. It is a true game changer. And this really brings us to a final powerful idea. This huge breakthrough didn't come from a better piece of hardware or some more complicated algorithm. It came from looking at a very old problem from a completely new angle. It really makes you wonder, doesn't it? What other impossibly hard problems out there are just waiting for the right shift in perspective to suddenly become solvable?